Thanks, Stéphane, for the nice talk, for a nice introduction to these kind of types of waves. So now, if anyone's got any questions, please raise your hand in the participants list. And then, so I see Chris, you've raised your hand.
I was wondering, wave attractors are often discussed in inviscid theory, aren't they? I mean, people often do sort of simulations and so on of inviscid fluids, look at wave attractors. If you're saying that you can sort of get enhanced dissipation each time you get a reflection, does that mean it may be more difficult to get a wave attractor when you need many, many reflections in order to develop the attractor?
I mean, when you have reflection, you do have, you create a correction, so you have enhanced dissipation.
Yeah.
I mean, is it strong or not? Strong. I mean, it's still. I mean, it depends how many reflections you need to get close to the attractor.
Yeah.
This is. I mean, it depends on the scaling. I have a Ekman 1/6 scaling here.
Yeah.
I don't know how far. If you need just a finite number of reflection to get, I mean, it's clearly the asymptotic problem need to be solved. But
yeah, well, exactly. But I mean, this
scaling in terms of Ekman 1/6 should appear somewhere. Is it the main feature? I don't know. But what I can say that Yoto, when he's trying to relate the eigenmodes of the viscous mode that you obtain from that are related to attractors, he do observe kind of scaling in terms of Ekman 1/6 in his relation for the eigenfrequency, which is not something which is selects the mode, but at least it is present in the structure. The structure, you do observe scaling, and this term in terms of Ekman 1/6 that appears in the structure of the modes for the term of the attractor. But I think, I mean, we need to work out a little more to find out the general structure of an attractor for geometry like a shell.
Yes.
This has not been done so far.
Right, yes. But I mean, it does suggest, doesn't it, that you can't go on to having more and more and more reflections in order to make your attractor more and more sharp, can you? Because you will lose energy then. So there's a natural limit to how sharp the thing can actually become, I would guess, from your work.
Yeah, but you
lose, which is determined essentially by the Ekman number.
Yeah, but when you get reflected, you can, when you get concentrated, but the amplitude also increase in a certain way.
Yeah.
So, but then the increase in amplitude when you are contracting is more important. I mean, it's order one effect. Whether the effect of the attenuation, I mean, the damping is not for the Ekman 1/6. So it's a weak effect from this point of view.
Yeah. Yeah. Okay. Yeah. Thank you.
Any other questions for Stéphane? Stephen, you had a question?
Yeah. So this is a question about the possibility of secondary instabilities within the shear layers. So clearly you have a strong velocity gradient across the shear layers, and they're very thin. I'm just wondering how high the Reynolds number would have to be for those shear layers to become unstable to secondary shear instabilities.
Yeah, I mean, there are perhaps, so you mean shear instability, no?
Yeah.
No, because you may have wave resonance with like a subharmonic resonance in terms of.
Yeah, I was just thinking of standard shear instabilities.
Yeah, I don't know actually, but this can be computed, like, I guess, quite easily, because we know the criterion for the shear instability is quite simple to get. So we have something very localized. So we have stronger vorticity clearly in this shear, and we can imagine that we may have shear instability. That's clear. And I guess we have shear instability for the Stewartson layers the same, which are present. I guess we can have the same thing here.
Yeah. I guess in the numerics you showed, I guess there aren't the instabilities because the Reynolds number won't be so high. Lab experiments, again, it might be that there aren't any secondary instabilities, but probably like in the ocean case, like the tide case with tidal beams, I think typically they do observe turbulence within the tidal beam. So I guess they have gone unstable.
Yeah, I guess this is so you have also something which is time varying. So this has to be taken into account when we do look at the shear instability.
Yeah.
It's not a simple shear. It's
an oscillating shear.
So typically you should have some growth rates which are smaller than the time variation of this shear. It will not have time to develop, I guess.
Yeah, I'm often thinking of the oceanic case with internal tides. So of course in that case, the period of the tides is 12 hours. So a secondary instability has plenty of time to develop during an oscillation cycle. Yeah,
you have larger scale also.
Yeah.
Okay. And but for the tide, clearly I think there are no results for the general case, but I guess this kind of internal shear layers with a self-similar solution should exist also.
Yeah.
But when you move an object, so far they have been used only for the far field, not for the field which is close to the fluctuating object. But I guess they should be present also. And,
okay, thank you.
Any further questions for Stéphane? So I did have a couple of things. That one of them I think was sounded like it was quite straightforward, but could you go over again why in the case when you had both a stratification and rotation, why you don't get an extended mean flow that extends over the kind of propagates out of the interaction region near the boundary? So it was one of your last slides, I think. So it's when you had the reflection from the boundary.
The reason
stratification and rotation in there.
Yeah, the reason is very simple actually, because you are not in the inertial frequency range.
Well, that's for the harmonic, you mean? Yeah.
Yeah, that's omega equals 0 is always outside this domain.
Yep.
So you have no propagation for the frequency equals 0 when you are both stratified and rotation. So you have
so in this case, you can generate a mean flow, but just in the location of the.
Yeah. You cannot. You have no propagation at this frequency.
Okay. Yeah.
Your equation is elliptic. You have a localized solution, and that's all.
Yep. Okay.
Yeah. You have no waves.
Okay. Yeah, that makes sense. So I had another question, which is related to something earlier on about the Stewartson layers. Is there a simple reason to understand why there are these nested layers? Is there a simple argument, or is there no simple argument, just a complicated mathematical one?
I have no simple argument,
okay.
And my hope
exists.
Yeah, my hope that is that we will not have the same for the shell, for the because this is very complicated. The structure clearly you have all these boundaries are talking to the other boundary. You have recirculations, and all the phenomena is very complicated, and the structure that you have here actually depend on all the structures you have on all these boundaries here.
Right.
In my case, the structure I have in the internal shear layer just depend on the nature of the singularity.
So it would be different if you had a spheroid or ellipsoid or something, do you think?
So I don't know what I will get, but for will I get something like that or not? It's what we are going to try now. And
right.
Simulation tend to to say that actually it's not that complicated. It should, maybe it's simpler for the rotating shell when you have a frequency which is different from 0. But we have to check that and confirm that. And but I have no simple argument to say whether we will have this or not in your case when we are close with close streamline. So close interval.
Okay, maybe that there are no simple arguments, I'm not sure, but I just like to have a simple argument to understand that, because it's not obvious to me why you get these nested layers. But yeah, they do come out from the analysis, but there's no simple idea for why you have it that I've seen either. So has anyone got any final question for Stéphane? If not, let's thank Stéphane again. So thanks, Stéphane, for a nice talk. And for...
Thank you very much.